In this video, we're going to talk about L'Hopital's rule. So L'Hopital's rule is a method to compute limits with the indeterminate forms 0 over 0 or infinity over infinity. Typically, when trying to compute a limit, you first try to plug in x equals a into the original limit problem, and if it turns out that the form of this expression here is 0 over 0 or infinity over infinity, L'Hopital's rule says that we can take the original limit and replace it by taking the derivative of the top and the derivative of the bottom separately, and then hopefully this new limit will be easier to compute. In this example, we're going to apply L'Hopital's rule to compute a limit. Okay, so the limit we're asked to compute is the limit as x goes to 0 of secant x minus 1 over x squared. So we'll see that this limit has the indeterminate form 0 over 0. So as for any limit problems, the first thing you do is plug in x equals 0 into the problem to see what the form is. So we check form by plugging in x equals 0. Okay, so plugging in x equals 0, you get secant of 0 minus 1 over 0 squared. Secant of 0 is 1, so the numerator is 1 minus 1, and the denominator is just 0. 1 minus 1 is 0. So we see that the form is 0 over 0. And now because we have the indeterminate form 0 over 0, we're allowed to use L'Hopital's rule to compute the limit. So let's use L'Hopital's rule. Okay, so L'Hopital's rule says to take the original limit and replace it by taking the derivative of the top and the bottom separately. The derivative of secant x is secant times tangent, and the derivative of x squared is 2x. Okay, so now this is the new limit. So now we have to try to compute the new limit. So again, we check by plugging in x equals 0. So we have secant of 0 times tangent of 0 over 2 times 0. Secant of 0 is 1. Tangent of 0 is 0. And then 2 times 0 is 0. 1 times 0 is 0. So again, we have 0 over 0. So what this means is that because this new limit is also 0 over 0, we have to apply L'Hopital's rule again. Okay, so now L'Hopital's rule says take this limit and then take the derivative of the top and the bottom again. To derivative of the top, so the top function is secant x times tangent x, which is a product, so we have to apply the product rule. Okay, so the derivative of secant x is again secant x times tangent. So using the product rule, we get secant x times tangent x, which is the derivative of secant x, and then times the second function, times tangent x, and plus the first function times the derivative of the second function. So the first function stays the same, and then tangent x, taking the derivative, is secant squared x. So that's the derivative of the top. The derivative of the bottom is 2. So now this is the new limit we have to compute. So let's simplify it first. So let's scroll down. So I'm going to scroll down for more space. Okay, so now we're trying to simplify this expression. So we have the limit as x goes to 0. Secant x, tangent times tangent, becomes tangent squared. And then secant times secant squared is secant cubed x. And then all over 2. Okay, so now this is our new limit. So again, we try to plug in x equals 0 to see what we get. So you have secant of 0 times tangent squared 0 plus secant cubed 0 all over 2. So what is secant of 0? Secant of 0 is 1. Tangent of 0 is 0. Secant of 0 again is 1. And then all over 2. So now if we compute this, this is 0, but then this is 1. So this is equal to 1/2. Now we finally get something that's not of the form, that's not indeterminate form. Because this is not indeterminate form, this is the actual value of this limit. So this whole limit is equal to 1/2. Okay, so to recap, we're asked to compute this limit. So we try plugging in x equals 0, get the indeterminate form 0 over 0. So we apply L'Hopital's rule, and then we see again that this new limit also has the form, the indeterminate form 0 over 0. So we can apply L'Hopital's rule again. So sometimes you have to apply L'Hopital's rule more than once to try to compute the limit. And then finally we get something that's just a number. And so this is the value of this limit, which is the value of all these other limits also. So the original limit is equal to 1/2.